let's get started. All right, so what's going on? Homework 1 is due tonight. Lab 2 demo is due tomorrow, end of your section. Slight change is that I've changed the order of some things here. We're going to talk about K-maps today, but only for sum of products. We will do K-maps for product of sums and with don't cares a little later, before homework 3. But I want to get to the material on the D flip-flops and sequential circuits because you need that for lab 3. So I want to start that on Friday. So I shifted those around a bit. Other than that, any questions? No questions. I thought there was at least one question. Yes?
Yeah, I just have a question on the homework. For 5C, it's asking me to complement the expression.
Yeah.
I was just wondering, because there's like multiple expressions, there's like a plus and like a multiplication, how would you like do that complement like in the first step?
Okay, so what is it? It's x z bar. It's kind of far away from me. plus x plus y bar. And then xy plus z barred. So this is the expression that's there, right? Yeah. So you simplify that. No, that didn't work. Why is that not showing? Document camera 1.
I think you were writing just above where the color is.
This one doesn't have a little window. Here we go. Okay. Okay, wait. No, I don't want to freeze. Okay, now we can freeze. All right. So this is the original expression here without the bar. So the reason I'm doing that is because in HTML I can't put a bar over the whole thing. It doesn't work. It just sits on top of the other bars and you can't read it. Okay, so for each one of these problems, you write the expression, complement the whole thing, and then simplify. Any other questions? Yes?
How simplified do you want it at the end? Like,
should be
can't do the Morgans anymore, or?
Should be a sum of products.
Okay.
And of course, if you have any terms that can be combined into smaller, try to do that as well. Yes?
Would it be wrong to simplify it a bit first and then complement and then simplify some more?
No, you can do that. It's not wrong. It's just like any kind of algebraic manipulations, there's different ways of getting to the right answer. Some are longer than others, but as long as they're correct, there's no problem. Generally, when you have this complement in here above something, one of the approaches is not to simplify this one, because when you simplify the overall one, eventually you'll end up with 2 bars here, and then they go away. So that's less work. But if you were to do this first, you could still get the right answer. Any other questions? Yes?
That was partially adjusting my sleeve, but just to double check, I was like thinking about asking questions, decided not to, but I'll ask anyway. You apply de Morgan's law in the same order that you would apply the operations normally. So in this case, you would apply de Morgan's law to
Wrong.
Wrong. I think I asked that.
Yes, it's a good thing you asked that. Okay, so let's say you have an expression a plus bc, right? How do you evaluate that? You would first and b and c. Still not? Oh. It's the autofocus I want to first.
Thank you.
Okay, so when you evaluate this expression, the order of operation says you and b and c,
Yes.
and then you OR that with a.
Yes.
So now let's say you complement the whole thing. So what do you think happens here?
Oh, it goes down to the OR.
So this becomes not a, and then complement b, c. Right, so we complemented this when we distribute the complement over the sum, right? A got complemented, and then we have the complemented. So we have a bar ANDed with BC bar, right? And then we do one more step, distribute this one, and we get a bar. And then this becomes a plus, and then we have B bar, C bar. So now we have A bar ANDed with B bar plus C bar.
Oh, so it goes in reverse order.
Well, so, when you're doing the OR operations, you're doing bottom up. This is do the ands first. When you're distributing the complement, you're going top down. So the last thing that you would do here is this OR. So it's the first thing you do when you break up the complement.
That makes so much more sense. Thank you so much.
Okay?
The tree really helps.
We like trees here. Santa Cruz and computer science. Okay. Any other questions? Okay. All right. So today is all about minimizing logic with K-maps. So let's talk about that. Okay, so we want to make small expressions. First question is, what do we mean by small? How do we measure our expressions? And we do that with a metric for expressions, which is the number of literals in an expression. Okay, so the number of literals in an expression is determined by counting literals. A literal is an occurrence of a variable or the complement of a variable. So if a variable occurs multiple times in an expression, we count it each time it occurs. So for example, let's do a couple of examples. How many literals in this expression? Yes? Three. Okay. How about this one? 5. Okay. This one? 4. I didn't know if you were raising your hand or you were saying 5. Either way, it's right. Okay. This one? How many variables do you see? 0. Okay. Yes, 7. Okay. So obviously some of these aren't as simple as they could be, right? In particular, this one could have been just equivalent to 0, so we could have had 0 literals. But we're just measuring the expressions as they are. And what we're going to do is try to minimize the number of literals. Because if we were to build a logic network directly from these expressions, without simplifying them, but directly, each one of those literals would be a gate input. Okay, and so that's a measure of how big our logic network would be. Okay, so our goal, we're going to restrict ourselves to sum of products expressions. Our goal is to find sum of products expressions with the fewest literals possible. Okay, so let's do an example. So this particular function happens to be the sum of minterms 2, 5, 6, and 7. Okay, and we can write it out as our canonical sum of products. Right, so M2 is 0, 1, 0, so this is A bar, B, C bar, etc. We did this last time. Okay, generally the sum of minterms is about the worst sum of products you could have. In fact, you can't really make it worse. So how many literals do I have now? 12, okay. So let's see if we can improve it a bit. One thing we could do maybe is we could factor out an AB out of the last two terms, and then our C bars or C becomes 1. And then, hey, how many literals now? 8. Okay, so we're going the right direction. We're down to 8. Okay, let's factor an A out of the last two. And now I can apply simplification. And, right, this is now B or C. And, okay, but I don't have a sum of products anymore. This is not a sum of products. So I'm going to distribute that A back. And how many do I have now? 7? Okay, I have 7. Okay, that's one better. Okay, I'm going to do this again. I'm going to factor B out of the first two. Simplification. Now I'm down to 6. Okay, and that's pretty good. Can I do anything else to this? Good questions. Those of you who are looking at the slides say, oh, yes, you can. This is not the minimum. In fact, this is actually a rule called consensus. But anyway, we could actually make this smaller. To make it smaller, we're going to make it bigger temporarily. And this is what happens in Boolean algebra. Sometimes if you make the expression larger, you can make it even smaller than before. So I'm going to end this middle term with 1. And then I'm going to introduce C, because 1 can be replaced by C or C bar. Right? Okay, how many literals now? 10. Clearly not going the right direction. We were down to 6 before. Okay, however, now what I can do is I can factor out a BC bar out of the first two and an AC out of the last two. Basically, this is absorption, and I'm down to 4 literals. Okay. So this is hard to see that this was the right thing to do, right? And what K-maps let us do is immediately see that this is what we should do. Okay, so how do K-maps help us see that we can get to 4 literals and not 6? All right, so here's our original expression, right? And we are going to look at the K-map. Where did my K-map go? And we are going to identify what we call an implicant. An implicant is essentially a product term. It's a product term that's 1 when the function needs to be 1. Now, it's not 1 everywhere the function needs to be 1, but it's 1 in places where we know the function is 1. Okay. The values for which the function is 1, remember, is called the onset, set of input values for which the function is 1. So if this is our K-map, right, we can fill in the function. It's going to be 1 for 2, 5, 6, and 7. And assuming I've labeled my K-map this way, it's simple to fill in the K-map because I can just put the ones in 2, 5, 6, and 7. Okay. Now, I want to identify rectangles or values or combinations of inputs that are next to each other for which my function is 1. So individual cells or minterms are places where my function is 1. All right, so these are implicants. They're product terms that are 1 when my function needs to be 1. But I could also make some bigger implicants that correspond to smaller product terms, doing essentially what we did before. So before we combined these two, remember we factored out the AB, and we ended up with just a product term AB. And in fact, that corresponds to merging those two cells. Right? This is minterm 6 is here. This is minterm 7. They differ by exactly one variable. One of them has a C bar. The other one has a C. So they're right next to each other in the K-map. And so instead of drawing these individual cells, I can draw a bigger one that covers 2 of them next to each other. And this is then the product term AB. Okay. So an implicant actually corresponds to a rectangle that only covers ones. And very important, its dimensions have to be powers of 2. So you can have a 1 by 1, or a 1 by 2, or a 1 by 4, or a 2 by 2, or a 2 by 4, or a 4 by 4. You cannot have any 3s. Do not draw any rectangles of dimension 3. And that's because they will not correspond to a product term. So the product terms correspond to rectangles whose dimensions are 1, 2, or 4. Okay. Are there any other rectangles here that I could draw? Yeah? BC naught? Okay, it's there. Okay, so these two are next to each other, and this is a nice 2 by 1. And this one is BC naught. That's the product term I get when I combine these two minterms. And then I also have AC. If I combine these two minterms, I get AC. So these are all implicants. They're all rectangles where my function is 1. Right? So these are all implicants. The thing is that I don't need all implicants. What I really want are just the ones that can't be bigger. So we're only going to be interested in drawing and listing what we call prime implicants. A prime implicant is an implicant that cannot get bigger. It's not inside another implicant. It's not completely contained in another implicant. So remember, here's my list of implicants. So these 3 were prime. BC bar, AB, AC, these are all prime. They're not inside a bigger one. Now you might say, wait a minute, AB is covered by others. But the key thing is it's not covered by a single other. It's not inside BC bar and it's not inside AC. So it's still prime, even though its parts are covered. Yeah? This one? Okay, so we're in B and we're outside of C. No, we're partly in A and partly outside of A. So A was not going to appear. Okay? All right. So from now on, ignore all implicants that are not prime. Don't even draw them. So when you start with your K-map and you try to draw large rectangles, pause and ask yourself, can I make this bigger? If you can make it bigger, don't draw it because it's not prime. Okay, so we're going to ignore all implicants that aren't prime. We just need the prime ones because our sum of products, our minimal sum of products will never use an implicant that's not prime. And the reason is that the product term of an implicant that's not prime will have more literals than the one it's contained in. As these rectangles get bigger, their product terms get smaller in terms of number of literals. Right? Each one of the min terms had 3 literals, and each one of these prime ones has only 2. So there's never a case where you would use a non-prime. You would not get a minimal expression. You could always replace it by the prime implicant it's in. Okay, so we only need to look at the prime implicants. Okay. Now, we have to pick enough prime implicants, enough product terms, to make sure that our function is 1. Everywhere it needs to be 1. Right? We need to get a sum of products that covers all the ones. So how do we do that? Well, the first step is identifying the prime implicants that are forced. So if a prime implicant is the only prime implicant to cover a particular cell, then we have to include it because there's no other choice. We have to have that, a prime implicant, in our expression. So here, there are 2 prime implicants that are forced, BC prime and AC. Those 2 are forced. Right? BC bar is the only one to cover cell 2, and AC is the only one to cover cell 5. So I have to include those 2. So right away, you know you need the forced ones. Those are part of your cover. Those are part of your expression. Sometimes you're going to need more. But in this case, have we covered everything? Yes. In this particular case, if I include BC prime and I include AC, I have covered all the ones. This is the sum of products with the minimum number of literals. Yeah?
When would you need more implicants than just the forced ones?
We'll see.
Okay.
We will definitely have some examples where that will happen.
I'm very curious.
Okay. Yes?
Would you ever need to rearrange the K-map in order to see implicants?
Rearrange.
Yeah, like, you know how it's like the order like 0, 2, 6, 4? Would you ever have to change it?
You can't change it. That's determined by the variables, right?
I thought you said you could change the order, like the arrangement of the variables.
Well, so this particular function talks about minterm 2. That's with respect to this order. So minterm 2 would be A bar, B, C bar. Right? Now, you can label your K-map any way you want, but minterm 2 has to correspond to the cell where you are outside of A, in B, and outside of C. All right? So the numbering here is determined by your labeling. It doesn't really matter how you label it in terms of finding the minimal sum of products. But how you label it depends on where you put your ones. Okay, so filling in the K-map, if we give you a sum of minterms, you need to label your K-maps and then identify which cell corresponds to 0, 1, 0 for 2, and 101 for 5, etc. But once you have a K-map, then coming up with a minimal sum of products is doesn't matter how you labeled it. It's not going to affect the result. Okay, all right. So, all right, so here's our procedure for finding a minimal sum of products. Step 1, draw the K-map. Okay, so this is where you draw your K-map, you label it, and you put the ones in the right place. Okay. If you label it some other way besides the way I'd labeled it, then you have to figure out where the ones go in terms of the numbering, because you're moving the numbers around. So I highly suggest you don't do that. But you can still get the problem right if you do. Once you've done that, you list all prime implicants. Just the prime ones. So you draw the prime implicants and you make a list of them. Now, this is where I'm going to emphasize all, in case it's not clear. It's tempting to say, oh, I can see I'm just going to need these two. But that's not the procedure. The procedure is to list all of them. If you don't list all of them, you cannot do step 3 correctly. So don't make a decision yet about which ones you're going to use. List all of them. Just the prime ones, though. Once you have all the prime ones, then you can go through your list and figure out which ones are forced. That's pretty easy because you just look for cells that are only covered by one of them. And then those prime implicants are forced. And then this is the fourth step, where sometimes the forced ones don't do the trick. Sometimes you need to include a prime implicant that's not forced. Okay, and we'll talk about how to do that. But before I do that, I want to talk about how you figure out what product term corresponds to a particular rectangle. So let's say we have this particular rectangle. How do we come up with the product term for it? Well, if we look at it, is it in the region where A is 1? No. Is it in the region where A is 0? Yes. So it's basically an A bar. Right? That purple or magenta rectangle is in the part of the K-map where A is 0. Okay. What about for B? Is it in B? Yeah. Completely in B? No. Is it completely in B bar? No. It straddles B bar. It straddles B. So no B in the product term. B does not appear. Okay. What about C? Okay, so it's in C. So our product term then is A bar C. Okay? So that's how you get the product term. Yeah?
Did you have an implicant from like cell 0 to cell 4 since you had the circular?
Yes. Okay. In fact, that one. You read my mind. Okay, so you got to remember that the right side of the K-map is next to the left side, so you can draw rectangles across that boundary. Okay, and this is a 2 by 2 that crosses that boundary. Okay, is it in A? Is it in A bar? No, okay. It straddles A, so A will not appear in the product term. Okay, is it in B? Is it in B bar? Yes, so it's going to have a B bar there. Okay, how about is it in C? It straddles. Okay, so what's our product term? B bar, right? And if you look at the values for each of these, you'll see they're exactly the 4 cells where B is 0. The middle, B is 1 here, B is 1 in these two. Okay, so that's how you get the product term from a rectangle. Okay, if you draw a 3 by 1, you won't be able to come up with the product term for it. Okay, all right, so I think we're ready to run our first one. Let me put the procedure here. All right, so there's our K-map. Did I freeze this? Focus out. Okay. Okay. So where do our ones go? Yeah. Right. So here our function is given as the product of max terms. So this is our offset, right? So I'm gonna put a 0 here and a 0 here, and as you say, everything that's not 4 or 7 is getting a 1. Okay, so that's the first step. Fill in the K-map. Oh, no, actually that's not the first step. What did I not do? Label. I should have labeled this, right? A, B, C. The numbering I have here corresponds to A, B, and C. If you change these, you'll have to figure out the numbers again. Okay. All right. Anybody see any rectangles? Yes. Okay, a 2 by 2. Okay. And what's this product term? Right? It straddles B, straddles C, and it's outside of A. Okay, any others? Yeah. 2 and 6. Okay. And what's the product term? B, C bar. Okay. Any others? Yeah. 1 and 5. B, okay. So here's the problem. If you say B not C, is that the C that gets the not or the B? you mean the B, okay. English is terrible. Natural language is terrible for expressions. Okay. Any more? Yes. No more? Yes?
Actually, no, since we did 0, 1, 2, 3, we can't do 2 and 3, right?
2 and 3 would not be prime. Right. Yeah. Don't ever draw anything that's inside another one. Parts of it can be in 2 others, but not completely inside another one. Only draw the prime ones. Right? PI stands for prime implicant here, not private investigator. Okay. Okay, so this is the other place where you need to pause, even though you're in a rush, and ask yourself, did I miss any? Because if you missed one, it may change the answer. Okay, I think we got them all. All right. Now, which ones are forced? Well, one way to do that is, well, look for cells that are only covered by one. So we have a bunch of cells that only have one choice. So this is forced because of 0 and 3. This one's forced because of 6. And this one's forced because of 5. So they're all forced. And this means that my expression will require that I take all of these. And have I covered everything? Well, I've covered those 4. I've covered those two, and I've covered those two, and that's everything. So, in fact, there aren't any others, so I'm done. Okay? Any questions on that? Okay, so which one was next? Yeah.
Instead of writing, like for example, instead of writing B, C bar, could you instead write A, B, C bar?
If I write A, B, C bar, that would be just this cell, right? So, if you want me to write A, B bar, C, well, how many literals does this have? Total. How many does this have? Yeah, so this is not minimal, right? This is, if this is why you never want to include something that's not prime, because you could replace that product term with the one that it's in, and you would decrease the number of literals. So if you're using an implicant that's not prime, you do not have a minimal sum of products. It can be improved. Okay? All right. Trying to remember which one's the next one, but okay. All right, so really quickly, let's talk about finding 4-variable K-maps. Remember, we did talk about 4-variable K-maps. We will not do 5-variable or 6-variable. Unless you really want to. No? Okay. So we're going to stop at 4 because I think that's sufficient to explain the concepts. And there's just too much bookkeeping involved in doing 6 and 5. All right, so very quickly, what is the product term for this implicant? Is it inside A? Outside A? Okay, so how about, is it inside B or outside of B? Straddling. How about C? How about D? All right, so what's our product term? Okay. All right. You can certainly have DA bar. Just, I like to keep them in order of the variables because that prevents me from listing one twice. But
That's a good strategy.
it's a strategy, but not required. Okay. How about this one? Here, I'll put it there for you. How about Marco? What? Yeah. A, C bar, D bar. There's no B, right? It straddles B. Okay. This whole top row is where C and D are both 0. So it's going to be C bar, D bar, and then we're inside A. Yes?
Is there a reason why you started off with a 2x2?
No? These are just examples.
But like, would we still get the same result if we would do like 2x1?
Yeah.
Like 1 5 and 27?
But those wouldn't be prime.
No, I'm saying 1 5 and 20. We did it for 2x2.
Which 2 by 2?
The 1 5 3 7.
Well, those, if I'm trying to find the product term for this 2 by 2, right? If this is an implicant, then 1 5 is not going to be prime.
Well, yeah, but I'm saying like if we didn't start off with the 2x2, like if we just didn't do that first step.
Why would you want to do that?
I mean, I'm just like wondering why.
I mean, you can combine them using the algebra we did before, but what you want to do is just draw it and immediately recognize that this is A bar D, right? I don't think you want to you don't want to come up with the product terms like that. It'll take you forever. Okay. All right. Next one then is this one. Okay. Here we go. All right. So this one we were given our onset. Oh, wish we'd been given the offset because it would be a lot shorter. But all right, so 0, 1, 2. So 0, 1, 2? No. Okay, careful, right? These are not in order. So it's 0, 1, 2, 3. 3's not here, so okay. No 4 and 5. And then we have 6, 7. So here, if you go 6, 7, you're still okay because they're both there. But in general, this is 6 and this is 7. And for 8, we have to go to the far column. All right, so we have 8, 9, 10, but not 11. Then 12, 13, 14, and not 15. Okay. See any rectangles?
Just so I don't have to do the math myself, where is the A, B, C, and D?
Oh, I did it again. Okay. A, B, C, D.
I appreciate it.
Sorry, I forgot. I just know they're there. They're supposed to be there. Yes. Okay, so we have this 1 by 4 here, right? And that is C, D bar. Yeah. Yeah.
12, 8, 13, and 9.
12, 8, 13, and 9. Okay.
Which is A, C bar.
A, C bar. Yeah?
Out of curiosity, could 12, 8, 13, 9, 0, and 1 be a larger?
Yes, and what would, that's a larger rectangle, but what's its dimension?
3 by 2, that's why it doesn't work.
No 3s.
No 3.
No 3s. 3s won't correspond to product terms. Yes, go ahead.
0 and 1.
Okay, 0 and 1. How many people think 0 and 1 is a prime implicant? No, why not? Yes.
There's a bigger one involving 8, 9, 0, and 1.
Okay, so remember the left side and the right side are next to each other. So these are the ones you're going to miss because, yeah, so this is where you want to be real careful. Before you draw one, think about it, especially if it's on the edge. Make sure you look at the other side and check that it can't be made bigger. Okay, this is a very common mistake. Easy to do. Yes? 12, 8, 14, or 10. Okay. So we have this one. Oh, wait. We didn't come up with a product term. What was the product term for this one? I'm sorry? Not B, not C. Okay. Now this one? All right. Who gave me this one? Yes. Okay. What's the product term? A D naught. Yes. A D naught. Okay, it's in A, straddles B, straddles C, and it's outside of D. Okay. Any more? Yeah. 6 and 7. Okay. And what is this product term? There's a C in it. What? BC. Okay, we got them all there. Okay. Any more? No? How many of you have been to Four Corners? How many? You know where four corners are?
Oh. Because those would be not, that would be B bar, D bar. And B bar, D bar.
Anybody been to Four Corners? You know what I'm talking about? Yes? Yes, that's where four states meet. Arizona, New Mexico, Colorado, and Utah.
The states.
Right, that's what I mean, the states. So these four corners are all next to each other, right? Because these two are next to each other, these two are next to each other, these two are next to each other, and these two. So this is my favorite prime implicant. And what's it called? Not B, not D. Okay. All right. Any more? Okay. The other point of danger. Forgetting one of them. No, that's it. Okay. All right. Now, which ones are forced? Okay. Now, if you've drawn all of them, then you can correctly identify the forced one. If you didn't draw all of them, then you might get this part wrong. That's why you have to draw all of them. Okay, so clearly this one is forced because 7's only covered by this one. And this is the only 2 by 1, so it has 3 literals. I can find it easily. Any other cells with only one choice? 1. All right, and that is B bar, C bar. So this one's forced. 13, okay. 13 is A, C bar. Okay, any others? I think that's it. Those are the only 3 cells that have just one choice. So far I have A, C bar plus B bar, C bar plus A bar, B, C. Then the question is that enough? So let me check. All right, so A, C bar covers those 4. B bar, C bar covers these 4. And 6, 7, that's A bar, B, C, covers these 2. Okay, did I cover everything? No. Okay, so this is a case where the forced prime implicants don't cover everything. So at this point, it's usually a very small problem, and you can easily figure out what the best solution is. Okay, I still need to cover 2, 10, and 14. Is there an obvious choice to do that? Okay, so in this case, CD bar is the only one that does all 3. If I don't use CD bar, I'm going to need at least 2 more. All right, so this is the best choice for the remaining. It's not forced, but it's the best choice. So there we are. Okay, how many of literals do I have? Okay. So this is how we come up with minimal sum of products. I suppose you want to do one more, right? No? Yes? You don't have anything better to do, right? Yes? I'm going to post these, so don't feel like you need to write all of this down. Oh, okay.
Go on. I do actually have enough written down that I can get the rest, but it was.
Okay, you can always rewatch the. Oh, by the way, on the videos, so I realized that the front-facing camera doesn't capture the podium, so I removed that video stream, so you only get the video stream from the projectors. Okay, all right. Should we do another one? Yes, okay. Okay, and this time I will label it first. Okay, so we have 0, 4, 8, oh, no, not, well, we will have 12, so that's okay. 0, 4, 8, 10, 11, 12, 13, and 15. We do not have 1, 2, 3, nor 5, 6, 7, nor 9, nor 14. Yes? Is there?
The function is x, y, z, and w.
And I thought I was doing it right. Come on. Okay. Oh. Okay, so again, the same order. You want to follow the same order. The order here is very important. Pay attention. If somebody tells you, hey, this is your function, you don't know what function you have unless they specify the order. All right, so this is x, y, z, w. Okay, thank you. What's next? Yeah. 0, 4, 12, and 8. Okay, you're going for the big one. Okay. This is y. You think there's a y in this? Right? So, I mean, a rule of thumb is a minterm will have all 4 variables. A 2x1 will just have 3 variables because you lose one. And then if you have a 4x1 or a 2x2, you should only have 2 variables because you've lost yet another one. If you have a 2x4, that's a single variable. And if you have a 4x4, you have 0 variables. Your function is all either just 1 or 0. Okay. Anything else? 8 and 10. Okay, the one that wraps around. And that one is x, w bar, now there's no z, right? Because it's partly in z, part outside. Right, okay. Yes. Okay. Okay. Yes. 13, 15. Okay. Yes. 12 and 13. Okay.
Y, or x, y, z bar.
Okay. Did you have one? Okay. Okay, any more? How about 0 and 8? Not prime. Okay, so that's actually inside here, even though it, you break it up the other way, it's still inside here. Yes, there was a question? No? Okay. 10 and 0? No, these are not next to each other. They're diagonal, but they're not next to each other. The only reason we could do it in the previous one is because we had all 4. Yes?
Why is 13 and 15 a prime if it's inside two different?
Well, is it inside another one? Is it inside one other one? It's inside 2. That's not, so it's still prime as long as it itself is not completely inside one other. Okay, so if I were to draw 0, 4, that would not be prime because it's inside this 4 by 1. But 13, 15 is not inside another implicant. Okay, so there's a difference between prime and forced. Is this one forced? Is 13, 15 forced? No. Okay, it won't be forced because all of its parts are covered. In fact, which ones are forced? Yeah, this is the only one that's forced here. So I'm going to start with Z bar W bar. And that covers just the top row. And now I need to cover the other 4 ones. What are my options here? I have lots of different options, right? I could include all of these. That's probably not a good idea. Yeah? Okay, so this is where you use your intellect and say, gee, I need to cover 4 remaining ones. Each one of these covers 2, right? Each one of these remaining prime implicates only covers 2. So I'm going to need 2 of them. And I can do it with these 2, so that's going to be optimal. So we're going to take 13, 15, which is X, Y, W. And we're going to take 11, 10, which is X, Y bar, Z. So together, these are the best choice for the remaining. So number of literals is 8. Okay. I do have one more, but I think you're probably exhausted by now. Any questions? Yes?
I don't think I heard, did you guys do
11, 10, that's, how many cells is that? 11, 10, and 8.
3?
No 3s. No 3s. Never draw any rectangles 3. Yeah. Okay. So so once you've got the forced ones, then it will be it often will be pretty obvious what to pick. But in this case, it's a little less obvious. But the argument we make is that, well, I've got 4 cells to cover. Each of these can cover 2. So the best I can do is to use 2 of these. Okay? And I can do it with just 2, so that must be the best. There may be other combinations, but we know at least this is optimal. Hi.
Does this look better to you? I did catch the one.
It does look better, yeah. Okay. Does that make